All right, so properties of limits. This is going to kind of culminate with the algebraic solving of limits. So we're going to do a bunch of examples. This is going to be a bit of a longer video. I might break it into two pieces, and there will be an assignment that goes along with this. So be aware there is some homework that goes with this video. So we've got a number of different properties that we need to kind of figure out what they mean, and then we can work with them from there. So the first rule is the sum rule. So this rule states that the limit of the sum of two functions is equal to the sum of their limits. So if I have two functions kind of combined here, I can break them up into their respective pieces. Okay, so this is especially apparent when we're looking at things like polynomials, and so we can see in this example that if I ask for the limit as x approaches 3 of, let's go with x squared minus 2x. I can then, and so sum also being difference, okay, so also applies to subtraction. Okay, because we can think of subtraction as adding a negative. We can then look at this as the limit x approaches 3 of just my first function, x squared, minus the limit as x approaches 3 of my second function, 2x. Now notice that because I've left that subtraction symbol here, that it's not attached to my actual expression that I've moved there. From here we can solve each one individually, so by just plugging in, because they're not non-permissible values. So we can go, okay, well, what is x squared when x is 3? Well, that is 9, minus the limit of x approaching 3 of 2x, so just plug 3 into there, so minus 6, which gives us a lovely total of 3. And so that would be my final answer to the limit. X approaches 3 of x squared minus 2x. Now this is a really handy time if you wanted to like bust out your graphing calculator to see if that was in fact the case. What's nice about using the graphing calculator to double check your answer is that once you've graphed it, if you press the trace button, then you can, or if you press second function trace, that's the calculation button, and then if you choose values, which is number 1, you can then choose your x value that you want it to determine, and it'll automatically tell you the y value. So I'll make another video showing you how to do that, but it's a great way to just double check your answers for when you're finding limits. Now, the extended sum rule is just basically that you can continue forever in terms of breaking them apart. It doesn't have to be just two pieces being combined. It can be any number of terms as long as they're being added or subtracted. You can combine them. The constant function rule. So whenever you're taking the limit of a constant, then the limit is a constant. So again, if we look at an example of this, it can literally be anything. So if I take the limit as x approaches 10 and my function is 7, my limit is going to be 7. And that applies for any constant value here. Okay, so that's a really, really big one. The limit of any constant is itself. So if we had gone back to that previous example and we had a trinomial with a constant term at the end, I could have still broken it apart, and that last term would have then just been itself. And that kind of makes sense when you graph it, because the y value is always the same if we're looking at a constant function. So this becomes apparent when we actually create a graph. So if I create a graph of my function 7, and I actually graph it, it makes a horizontal line. So no matter what my x value is, my y value is always 7. And we see that in our table here as well. So that's further proof. So while I have you here, I may as well show you how to do that other piece. So again, if we wanted to graph that function and it was x squared minus 2x, we could graph it. Gives us our lovely picture. First of all, it creates some values on our table of values, so that's one way you could check. But if it's maybe not on your table of values or it's not in the picture, what you do is second function trace. You choose that number 1 value and you enter your value. So we were looking at x is approaching 3, so we plug it in and it tells us that y is in fact 3. So again, that's how we can kind of use the graphing calculator to our advantage, especially when doing calculations. So on to the next rule, constant multiple rule. So this one's kind of interesting, kind of ties in with the next rule in the same way that the constant function rule works. So what you see, I'm going to jump down to the product rule for a second, is that the product of any two functions is the product. When you're taking the limit of the product, it's the same as the limit of each of them multiplied together, assuming the limits exist. So when we look at the constant multiple rule, what they're basically saying is, well, if you take the limit of the constant, just remember that it is a constant, so you basically just can bring the constant out in front. So again, if we looked at something like the limit of x approaching 0 of 3x cubed, that would be the same as saying 3 times the limit as x approaches 0 of x cubed. Okay, and so again, bringing out that constant from inside the limit to outside the limit. And in this particular case, that would be 3 times 0, or just 0. And again, you can check that on your graphing calculator. So our product rule in general lets us break it apart the same way we break apart addition and subtraction. We can break apart multiplication. So when we see the limit as x approaches negative a half, y negative a half, because why not? We've got 3 of 3x squared times 2x minus 1. We can break this down significantly. So, excuse me while I scroll over. So the product rule basically says, well, I can chunk it into limit as x approaches negative a half of 3x squared times the limit as x approaches negative a half of 2x minus 1. Again, you can put brackets or not. And from here we can even break it down a little further. We could pull that 3 out using our previous rule. Limit. We could break this one apart even further. X approaches negative a half of 2x. 2x, and then just subtract 1, because remember the limit of a constant is itself. So if I take the limit of that half, that's what I would get. And from here, it's just a little bit more of algebra. So negative a half squared is 1/4, so 3/4. And then we've got negative 1, subtract 1 is negative 2. So we end up with negative 3/2 as my answer. And again, especially while you're first starting out this, if you want to check yourself, if you want to take extra time to actually do those calculations, you're more than welcome to. Just be very, very careful when you're plugging in numbers to make sure you get rid of this limit and x approaching a value as you're plugging in to x, because we're not taking the limit as it approaches -1/2 squared. We're taking the limit of x squared as it approaches that. So just be conscious of that when you're showing extra steps there. So again, we saw extended product rule. If I'm multiplying multiple things, I could have also taken it to be just like the limit of 3 and the limit of x squared, and again multiplying those out in the same way that the sum rule works. Quotient rule is again pretty much the same. It just lets you break things apart. So if we look at this example, if I asked for the limit as x approaches 2 of x to the 4 plus x squared minus 1 all over x squared plus 5, and that was all the function that I was working with, then what I could do is I'm totally allowed to break it up into a numerator limit and a denominator limit. So my first step would be x approaches 2 of x to the 4 plus x squared minus 1 all over limit as x approaches 2 of x squared plus 5. From here I can start to use other rules too, so that sum rule again comes into play. So I've got the limit as x approaches 2 of x to the 4 plus the limit as x approaches 2 of x squared minus 1 because of the constant rule. And in the denominator, limit x approaches 2 of x squared plus, and again, constants are unchanged by taking the limit, so I'm going to skip that step. So finally, 2 to the power of 4 is 2, 4, 8, 16, plus 4 minus 1 all over 4, because it's kind of nice, they show up twice, plus 5. So we get 16, 20, 19 over 9 as my final answer. And again, I could check that on my graphing calculator to make sure that I'm right. So the power rule is, again, just taking that idea of being able to kind of shimmy your limit into other pieces. So it says that for any limit where you're taking the limit of a function with an exponent, we can actually insert the limit and apply it directly to the function and keep the exponent on the outside. Okay, and the same thing applies because radicals can be rewritten. If we remember, if I have anything, I should call it, if I have any function under a radical, then I am totally also allowed to write that as f of x to the power of 1 over n. Okay, so because of this property and how they're related, this power rule actually also applies to radicals. So if you're taking the limit of a function that has a radical being applied to it, you are also allowed to squish your limit inside. Furthermore, because if f of x is equal to just x to the power of any number, this is just a special example, so it will just be equal to subbing in that value. And that's kind of what we already have seen as we've worked through this algebra. So again, if we want to look at an example of this power rule, we're going to have to kind of work in some confines here. So we can see this if we take the limit of x approaches -2 of x minus 6 to the power of 2/3. Okay, so again, because it's an exponent, even though it has a denominator, that's still meaning radical, and this rule still applies. I'll just work directly downward. So we can say that this is equivalent to the limit as x approaches -2 of x minus 6 all to the power of 2/3. So then from here we could just plug it in, or we could kind of break it up even more if you wanted to into x, and it's constant, but because x is just x, I'm going to work from here. So plugging in -2 in here would be -8. And then 2/3. Well, 8 is the perfect cube of -2, or -8 is the perfect cube of -2. -2 squared is 4, and so that would be my final answer. So that's how we apply the power rule. So again, it doesn't matter if there's a denominator, it doesn't matter if it's in radical form. If you want to rewrite the radical as an exponent with a rational exponent, you're more than welcome to, but it applies in both of these circumstances. Our limit of an exponential function becomes a little bit more tricky. So this is saying when the limit of x approaches a, and a is also the base of the exponential function, then it allows us to do this. So the base can be anything greater than 0, not equal to 0, because we can't really take the power of 0, just be 0. Okay, so that would be our one big restriction on this one. And then logarithmic, our limit again kind of sneaks in. So this is kind of like a function within a function, and it's allowed to sneak in, and you can take the log of it afterwards. So where you're going to potentially see function in the exponent is dealing with the letter e, which we know is a constant associated with the function of a natural log, or ln as some people refer to it. So our example today will look at exactly that. So if I asked you for the limit as x approaches 0 of e to the x cos x, and I'm wanting to include trig in this, so bear with me here, so I want to draw your attention to it as well. Then we can break this apart and we can use our product rule. So the limit as x approaches 0 of e to the x, and the limit as x approaches 0 of cos x. From here we can break this apart further, and now we can say it's actually e to the power of the limit as x approaches 0 of x times the limit of cosine x as x approaches 0. From here, well, we can just plug and chug. So we've got e to the power of 0, which is 1, and we've got, when we fill in 0 for cos, that's also 1. So 1 times 1 just equals 1. And love it. That's our answer. Okay, so that's one thing to bear in mind. When you're working with trig function, there is one particular special case that I want to draw your attention to. And it didn't show up in this example, but it can show up sometimes when you're working with trig functions, is that the limit as x approaches 0 of sine x over x is 1. And we can dive a little bit more into this a little bit later on, because the problem is right now, if we just plugged in, we would get 0 over 0, which is no good. So just use this rule as exactly that, and we'll come back to this later. Okay. So our last law is the limit of a log function. And so again, we're looking at specifically constants, and we're going to come back to this more and look at it through the lens of infinity and looking for horizontal asymptotes and endpoints rather than at this point in time. So you've got a number of examples. This was not nearly as long as I anticipated, so that's great. And I hope that you're able to attempt these questions and understand them and give the homework a shot. And if you have any questions there, you are more than welcome to email me or use the peer contact part of our 1-0.